All right, hello and welcome back. And before we go on to doing new things, I thought I'd just take some time and repeat some of the things that we tried to last time around. So I'll be trying to write here and let's see if we can get some. Okay. So what I want to do is I want to try and give you an idea of what is called active rotations in 2 dimensions so that we can clarify a bit about the clarify the discussion that we were having about the generators of SO2 just to make things a little clearer for you guys. Okay, so that's the idea of the first few minutes of this class, and then we will try to move on to other things after a bit. All right. Okay, so we will start off by saying a little bit about active rotations. And so we have a physical system, and we are going to look at, so you see here, for example, that I have a system. So we are looking at a plane here, active rotations on a plane. So physical objects are rotated about this origin. Uh, the coordinate system remains in its place. This indicates, indicates the situation before. I have rotated it in this afterwards. All right, so let me try and explain this a little bit. So an active rotation of a two-dimensional plane over an angle alpha around the origin of the coordinate system in the plane. This is going to be defined as a linear transformation of the plane into itself, which rotates every vector of the plane over an angle alpha. The point to note is that the coordinate system is going to still be in place. Okay, so the linear transformation. Let's just write some of this down. So an active rotation R of alpha of a 2D plane over an angle alpha around the origin of the coordinate system of the plane is defined as the linear transformation of the plane into itself, which rotates the vectors or each vector of the plane by an angle alpha but keeps the coordinate system in place. This is to be distinguished between something called a passive rotation, which is going to just rotate the coordinate system and not the vectors on the plane. We will actually not be that interested in passive transformations, but you all I mean you come across this active versus passive way of looking at things in a lot of places. So I urge you to have a look at this at some point. Now, the linear transformation alpha is fully, fully sort of clarified once the, images of u1 primed and u2 primed of say the two of vectors, say the u1 and u2. So once you okay, so let's again write this down. So the linear transformation, so R alpha is fully characterized once you give the images of the vector. Once you give the images of vectors, say u1 primed and u2 primed, of the original vectors, of the unrotated vectors u1 and u2. So let's say for the moment that u1 and u2 are given by e1 cap and e2 cap. So then so u1 primed is going to be, so let's say u1 is equal to e1 cap, u2 is equal to e2 cap. So that essential, so this and from here, let's say the images of the vectors are u1 primed, so there's rotated by an angle alpha, so e1 cos alpha plus e2 sine alpha, and e2 primed is minus e1 sine alpha plus e2 cos alpha. So these have been rotated by an angle alpha. So now suppose you are looking, so these are what has happened to our coordinate system, if you wish. So if you have, this is what has happened to our unit vectors. So now suppose you are looking at an arbitrary vector. Look at an arbitrary vector. So let's call this arbitrary vector v, which is v1 e1 plus v2 e2, right? And the image of v, so you now need to figure out what the image of v is. So and the image of v is w. Okay, so w is given by omega 1, so w1 e1 cap plus w2 e2 cap. Now you want to express this in terms of u1 and u2, u1 primed and u2 primed. So what do you write? So w essentially is v1 u1 primed plus v2 u2 primed. Remember that the u1 primed and u2 primed are what e1 and e2 have changed into. So now you can just write this down And then this is going to be, once you just plug in the above stuff here, so this is going to be v1 cos alpha minus v2 sine alpha into e1 cap plus v1 sine alpha plus v2 cos alpha e2 cap. So now what have we done? So if we see this, it's clear that now we can deduce the relations between the components w1 and w2 of this rotated vector with the components v1 v2 of the original vector, right? So w1 w2 is going to be given by something which is clearly cos alpha minus sine alpha cos alpha of v1 v2. So this is nothing but r alpha of v1 v2. Okay, it's an elaborate way of trying to get something that we have already, that we already know. But so now what we see is that so what we want to understand is how exactly these active rotations are going to affect what we are trying to do. So r alpha, as you can see, is these are represented. So in active rotation in the space of space of components of two-dimensional vectors is represented by this matrix here. Okay, so this particular matrix that I have here, that represents r alpha. So an active rotation in two dimensions is a rotation of the position vectors of the plane with respect to a fixed coordinate system. Okay, and what we see is that in this equation relates the components of the original vector to the components of the rotated vector in a fixed basis. That's what is important. One way to sort of visualize this is to imagine and trying to take a piece of paper and you try and draw some coordinate systems on it. Say suppose you have a point on the paper here, which we gave with the point P here. So this point P. So this is characterized by the position vector r before before rotation of the sheet. After rotating the sheet over by an angle alpha, which is what we are doing now, the same point on the sheet moves to another point, which is P prime. Okay, the point on the sheet is now characterized by this position vector r primed, which is given by r alpha times r. So this is given by, so r primed here is given by r alpha times, so r primed is given by r alpha times r. Now suppose we have replaced this sheet of paper by a sheet of metal, and we heat this in one corner such that this whole sheet has some sort of some temperature, which is function of where we see it. So here you have some t of r, if you wish. Okay. Now, in this new situation where you have uh, rotated the sheet, the function which describes the same distribution is a different function of position. Say that is t primed of r. But I mean this we will assume that this rotation of the sheet does not change the temperature at a given point in P. So what has happened is that there is going to be a relation between T and T prime. So let me again sort of write this down for you. I mean, I have said this in words, but let me write it down. So mm, yeah, the first thing that I wanted to do is say, you know, so I have explained what is the figure P. So now heat the sheet, heat the metal sheet such that temperature is a position dependent quantity, position dependent function, T of r. Okay, and assume that the rotation so after the after you rotate the sheet, the temperature distribution remains the same. But in this new situation, this is given by another function T primed of r. New distribution in new, not distribution, new function in rotated sheet. Okay, the distribution stays the same. I mean, so the temperature distribution stays the same, but when we have rotated it, since the r's have changed and so on, it's a different function of r. Okay, so now you have this following relation between t and t primed, which is t primed of r alpha of r is equal to t of r. So this is going to represent the same point, and so the same point in terms of the sheet that we have out here. This marked point here stays the same, so the temperature at this marked point stays the same, but they are represented by two different functions. So what do you have? You have t primed of r alpha acting on r is equal to t of r. So this is equivalently t of r primed is t of r alpha inverse of r prime of r. Yeah. So that is what this is. So what is happening? So in a function, in the functional space, the active rotation, so in function space, the active rotation R of alpha induces the transformation R of alpha takes you from F to D of R alpha of F, where D of R alpha of F of R, if you wish, is equal to F primed of R, which is now given by F of R alpha inverse of R. The reason why I went through all of this in just repeated all of this for you is that it's important to sort of reflect on the fact that this here is an inverse, and the fact that it is an inverse is something that I wanted to highlight to you. Okay, so this is something that we did last time. I did it very hurriedly, so I thought I'd just repeat this. And as I mean, consequence of this, what we will find is the I defined for you what the generators of SO2 are. So let me actually try to just go back and show you what this is once more. So I mean, as we did last time around, so let me just repeat this a little bit as well. Um, so the generators of SO, so repeating this a little bit, so generators of SO2, generator of SO2. So we saw last time around that what we did was we found that this guy was given by A was dd alpha of R of alpha, where alpha equal to 0. And this just turned out to be 0 minus 1, 1, 0. Okay. Right, and we also saw that R of alpha was exponential of alpha, right? This is what we saw last time around. Um, so the representation of the d alpha for group elements R of alpha of SO2 can be translated into a representation of the of the generator of the group as well, right? So now, so I mean, yeah, this is also something that we did. So d of R of alpha, which we in shorthand denote by d of alpha, this was given by exponential of alpha of d of a, where d of a is a representation of the generator of the group. This is a representation of generator of the group. Okay, and the result that we found was dk of a. This was just given as minus ik, and k was 0 plus minus 1 and plus minus 2 and so on. Now, the thing that I wanted to actually go back and clarify, for you was I mean, differential form of the generators. Okay, I think this was a little fast. Differential form of generators. So the idea essentially is, now that you know this, the idea is that d of alpha of f, where this is a function of r which is equal to xy, this is going to be given by f of r alpha inverse of xy. Now it should be clear now why we have an r alpha inverse instead of just r alpha. So the left hand side of this relation can be written in the corresponding representation of the generator, which we have just written down. So d of alpha f of r is equal to exponential of alpha d of a f of r. So this is the left hand side. And the right hand side of the equation is, now the right hand side, what we are doing is we are expanding this guy. Okay, so we are going to expand this guy. So this is f of r plus something. So this has moved a bit, right? So this is, let's say, delta x and delta y. So you can expand this guy. So how do you expand this? So you look at this. So you know, this is just you. You can look at. I mean, you can just try to yeah, do it. Sort of, yeah, component by component as well. But this is straightforward, right? So this is delta x del x plus delta y del y acting on f of r plus the higher order things as well. So half of whatever this is, delta x squared del 2x squared plus twice delta x delta y del 2 del x del y plus delta y squared del squared del y squared f of r. Let me move this around a little bit so that things don't get messed up. Now, what we do is we take this and so let's call these some things. Okay, let's say um, let's call this equation 1, and let's call this equation 2. And what we do is we'll expand this series. Okay, expand 1. So expand 1. So if you expand 1, what you get is d of alpha f of r is equal to 1 plus alpha d of a plus alpha squared over 2 dA squared plus dot dot f of r, of course. And if you expand 2, what you get is, so delta x, so expand 2. When you expand 2, what do you get? so you need the expansions of so what would we want to do? So we want to understand what delta x and delta y are. Yeah, so this so you need to start off with this, and what you need to do, uh, if you were to expand, 2, before you expand 2 you need this. So let's not write before this. So let's what we do is, let's say, so if you will need what this guy is. So what is this? This is r of so remember what this was. So this was r inverse, right? So this was r inverse, r alpha inverse of r. Also there's minus r, right? So you remember that was the first thing to do. So r alpha inverse is nothing but r of minus alpha, right? So this is something that we know from earlier. So this is just these two guys. And r so you again, so what we have is cos of alpha, um, as we know from before. So this is the matrix R that we have. This is the matrix R which we have, and we need to turn the alphas around. So what we'll have is cos alpha minus sine, plus sine alpha minus sine alpha, cos alpha, acting on uh, delta x delta y minus delta x delta y, right? So that is what we will have. And now again, what we need to do is we need to take alpha as being small, and hence so cos alpha is going to be 1, going to be approximated by, so this is going to be, so expand, cos alpha is going to be 1 plus dot 1 plus alpha squared, sine alpha is going to be alpha, and you put these back into the equation. So what you are going to get is you're going to get delta xy. Sorry, this is not delta. So yes. So this minus, so these are not deltas. So let me erase this. So this is xy, and this is xy, and this is also xy. There are no deltas here. Once you do this and put this back in, what you'll find is delta x, not by, delta y is given by alpha y minus alpha squared over 2x plus dot dot dot, and this is minus alpha x minus alpha squared over 2y plus dot dot dot. So these are uh, the forms of delta x and delta y. So now you can plug back. So now plug back in 1. What was it? In 2. So if you do that, then what you'll find is that f of r of alpha inverse r is equal to f of r plus alpha of y del del x minus x del del y. Maybe let me just take this downstairs. Sorry. Into f of r. So you see that this guy is going to be the generator. So this guy is going to be the generator. So d of a, if you just compare this with the above, if you link this up with what we have here, then d of a is clearly given by y del del x minus x del del y. Okay, this is something that I thought I should clear up, and rest of the things stay the same. I think this part was very rushed last time around. So again, if you take x, y as r cos theta, r sine theta, then this is going to be, so this is equivalently equal to del del phi, del del phi. Okay, so this is why so this is referred as, sometimes referred as the, I mean, del del phi is referred as the generator of rotation. So what we have done here is we've just done this, cos phi and y is equal to r sine phi. So if you do this, then this is given by minus the del del phi. Okay, so that was that. That was trying to repeat what we did last time around. So this was so what we will be doing in the second half of this lecture, or the next lecture if you wish, is moving on from SO2, which we have done in the last lecture and this one, and moving on to SO3 and so on. And things will get more interesting. This just had one particular generator, so there was no algebra to speak of. But yeah, after this, things will get more interesting. Okay, so that's it for now. We will see each other very shortly, and let's see. I hope this helped clarify some things which I had to rush over last time around. And yeah, so that's that. Thanks, and we will stop here now.